So the next speaker is going to be Ernst Hauber. So Ernst, are you ready to go?
I'm ready to go.
Okay, so the floor is yours. Yeah, we hear you.
And can you also see my screen?
Yes, please go to full mode. Oh, okay, full screen. Very good. Okay, perfect. The time is for you. Go ahead.
Thank you, Patrick, and good late morning to everybody. This is, so to say, a complementary talk to the previous one. We are also interested in INAD, in this irregular Murray patch. But what I'm going to do now is to present a landed mission to INAD. It's important to note that these two approaches are not mutually exclusive. We do not compete, but we would perfectly complement each other. So my name is Ernst Hauber. I'm a geologist working at the German Aerospace Center. Not the only author, of course. At the bottom here, you see all the co-authors. So how come that we are so many? Let me give you a little bit of background on this entire idea. So it's now 2 years ago, I think, that there was an ESA call, Ideas for Exploring the Moon with a Large European Lander. And we submitted originally an idea to explore INAD with a landed mission. And that's the blue authors at the bottom. And later, ESA established some topical teams. One of these topical teams related to EL3 was tasked to identify lunar geological mission concepts for EL3. And this team exists since 2020. That's the green authors. And so far, we identified 3 interesting geologic missions. They are all focused on volcanism. And if you're interested to learn more about that, there was a poster by Maria Cristina de Sanctis, who leads this topical team, and talks by Sebastian Bess and Harald Hiesinger, who introduced or explained 2 other mission scenarios that could be realized from a geological point of view, from a geological volcanological point of view by EL3. Now, in this study, we identified a relatively easy to implement EL3 mission. So it could be, if it is realized, it could come early in the EL3 program before we progress to more difficult or more technologically challenging ideas. The idea was also to collect and use as much European technical heritage as possible. And of course, last but not least, science should be what matters. So we address, in quotation mark, relatively simple yet fundamental question in lunar science. And the last group of co-authors, Jim Headliner, Wilson, and Lek Yao, recently published a number of papers of IMP science. So we were very lucky that they were kind enough to join our team. So that's how we came together. The case for a visit to an irregular Murray patch with an EL3 rover is twofold, so to say. There's a science interest. Petter has already nicely explained why and how irregular Murray patches are some of the most enigmatic surface features on the moon. There are 2 very fundamentally different formation models, and Petter has covered that as well. And since, of course, in advance of this conference, we knew about and coordinated our talks, I do not go into that in detail again. We have the old versus the young model. And depending on that, the results, either way, would have strong implications on the evolution of the lunar interior heat production and also the magmatic history of the moon. In terms of technology, the bonus is we would have a relatively simple landing on Mare basalt plains on the near side of the moon, so communication wouldn't be a big issue. We can see where we are. Since these irregular Murray patches in INAD includes that or is the same, the driving distances are very short. So we don't need to think about tens or even hundreds of kilometers. This is doable. And since it is a relatively short driving distance and what we want to do can be done in a relatively small space, we might not even need nighttime survival, which would also contribute to making this mission simple. Simple is always to be seen in a relative way. The payload would be interdisciplinary, so we would have a nice combination of geological and geophysical methods that would contribute and would be combined to solve these questions. You saw this left image from Peter's presentation. INA is a depression on top of a shield volcano. On the lower right, you see where we are. This shield volcano is one of the largest on the moon, and the summit is characterized by this depression in which we have a certain interesting number of different landforms. Here you see a close-up view on the left side taken with the Lunar Reconnaissance Orbiter camera. You also see the size, it's about 2 to 3 kilometers, not very large. And on the right, you see a blow-up. You see that the smooth surface is actually a positive topographic feature, a mount. This is called Mount or Monsagnes. It's a few hundred meters in diameter. It has relatively steep sides. It's often, the topography is often described as meniscus shaped. And this is surrounded by more rough, light-toned materials that make up the rest of the floor of this depression. The entire thing is a depression, and inside the depression, we have a rough floor and these mounts. Now, I don't go into the details here. I just would like that you focus on the 2 yellow boxes. So I mentioned before this, the young and the old model, and you see it's not a it's not a minor difference. This is a huge difference. So it's less than 100 billion years versus 3.5 billion years. In other ways, it should be possible, even if we have only instruments with a relatively limited precision or accuracy, it should be possible to distinguish between these 2 models with a huge age difference. I come to details later. So if we have a landed mission using the EL3 lander to explore INAD, what are the science requirements? On the left, I list a lot of science questions ranging from the geological context, from 3D morphology, over the age, composition, then the volatile inventory, because part of the hypothesis say that there was a contribution of pyroclastic volcanism to IMPs, and that would open up the perspectives for ISRO. Then we would like to investigate the thermophysical properties, densities, and the subsurface structure. So we have different measurements, and on the right you see the instruments. I don't go through all of that in detail, but I point out that the most challenging and new type of instrument is probably an in situ dating device, possibly with potassium argon. And I don't know if you followed the chat where Romain and Susanne Schröder talked about the accuracies of potassium measurements. And I think, and we discussed that in the topical team with Romain, INAD would be an ideal test case for such an instrument, because we don't have to be able to distinguish age differences of 5% or so. Even a coarse resolution of such an instrument would perfectly do the job. So it's an ideal test case for in situ dating. Importantly, and this is shown here, we address new and exciting science objectives. This is fundamental to get new ideas or confirm existing ideas about the lunar thermal evolution. But overall, we do not need completely new or game-changing technologies in terms of instruments. We can make use of existing heritage to a large degree. And in the boxes below, you see where this heritage exists. And if you're interested, you can maybe later on, I don't go through all the numbers here, but you see that we have already quite a detailed idea of the resources that are needed, the dimensions and the mass of these instruments. So we do not have to start from scratch here. The only exception is maybe in situ dating. I mentioned it already. This would be the major challenge in terms of instrument evolution, but it would be an extremely good study case, because this is where such an instrument could start perfectly. Before then, we go to more complex challenges. So for the mobility concept, initially we started thinking about a rover with a robotic arm, and that would still be the preferred solution. If for any reasons a rover wouldn't be available due to time or funding or technology reasons, we could also do a lot of the science with a stationary lander that could maybe deploy secondary small mobile elements. I will present a nice example later on. So the payload is based on heritage from European and international missions, most notably ExoMars, of course. For example, let me go through quickly a few examples. One that exists at DLR is a geophysical instrument, a radiometer for thermophysical measurements. There we have a rich heritage.
2 minutes left, Ernst.
How many?
2 minutes.
2 minutes, okay. So I skipped that. You can read that later. I think the talks may be available or not. But here you see for geophysics and geology, the existing heritage. Accessibility, Peter has already shown that. If we can land on Mare plains, that would be relatively easy. It's flat, it's on the near side, doesn't need to be precision landing. We would land there. The major challenge in navigation, from a navigation perspective, are the slopes, because these are partly steep. You can see that on the right side. And that may present some challenges for a conventional rover, and that certainly would have to be looked into detail. And I will show you one of the possible solutions in 2 slides from now. Very shortly, we can have a rover or a lander. The rover, this is just a model traverse. There are other traverses discussed in more detail by our co-author Lei Qiao. This is a model traverse, and you see it's only a few kilometers long. Should be doable without lunar nighttime survival. And on the right side, we would have a stationary lander, and that stationary lander could hopefully deploy some secondary payload elements that are mobile. And one of the examples is here. This is one that is being developed by our colleagues from DLR in Oberpfaffenhofen. It's called Scout Rover. It uses the principle of a rimless wheel. You see a wheel on the right upper left side. If you remove the rim, it's a rimless wheel. These spikes would be flexible, and you can see what kind of rough terrain this type of device is able to navigate. And this would be perfectly for a rough volcanic terrain. So it's amazing. There are movies on their website. It's amazing what this thing can do. It goes far, far beyond anything that is possible with a normal wheeled rover. There are other concepts like hoppers. All of that would do. On the lower left side, you see that this Scout Rover, it's not a mini thing. It can carry quite a number of payloads. So this would be a really nice solution for a lander with a secondary mobile payload. Summary slide. So we suggest to use the EL3 rover to first ever visit an appealing and enigmatic feature on the surface of the moon. We would address fundamental science questions on lunar thermal evolution. It would be an ideal test case for in situ dating. We have a nice combination of science payload, making use of a lot of technological heritage on the European side. It is a mixture of easy requirements and some challenges. Remember the slopes. It would be in synergy, if we are allowed to dream, with the mission that Peter has introduced in the previous talk. And I think it could be a good start for science with EL3 before progressing to more challenging scenarios. And in June, very soon, there will be an ESA contemporary design facility which studies the 3 geologically focused EL3 missions that we investigated in this topical team. And we are very much looking forward to see how feasible these ideas were, and if it's indeed possible to realize a mission like the one that I proposed. Thank you.
Thank you. Thank you, Ernst. That's a fascinating project, of course. We have to move quick, but one very short question maybe from Bernard Foin in the chat is there another way to determine age on this enigmatic feature before the mission?
That's a good point. I forgot to mention that another way to very coarsely determine the age would be to measure if these rocks are magnetized, because the lunar dynamo is supposed to stop somewhere between the 2 end member ages that I presented. So if these rocks are not magnetized, they would be young. If they are magnetized, they would be old. Before the mission, I don't know, because the magnetometer would have to have a relatively high spatial resolution. So ideally, this would be on the mission as well. And it was, if you look closely, it was included in our model payload. Does that, I mean, I hope that is sufficient as an answer for the moment.